Welcome everyone to our video on Introduction to Chemical Equilibrium. In this video, we will define what chemical equilibrium is. We will explain what's going on in chemical equilibrium from a kinetics perspective. And we will look at what conditions must be reached in order for chemical equilibrium to occur or to be maintained. You've probably heard the word equilibrium in other subjects or in just everyday common language before. Chemical equilibrium has many of those same characteristics. However, chemical equilibrium is really referring to a very specific phenomena when it comes to chemical systems. Chemical equilibrium is a state that a reaction or reactions reach where the composition, and when we say composition, we mean the moles of reactants and products, remains unchanged over time unless we disturb it. So once again, chemical equilibrium is a state where the composition remains constant unless it's disturbed. Before we delve into that definition a bit further, let's just introduce some notation and some language that you'll be using throughout this unit. Because an equilibrium involves both a forward reaction and a reverse reaction, we will use the term system rather than chemical reaction to describe all of the chemical species involved. In our reactions, because we have reactions going in both directions, instead of using the one directional arrow, we will use the equilibrium system arrow, which looks like two half arrows. Our chemical equations start to look something like this. Here we see the forward reaction of A and B forming C and D in the traditional left to right notation that we have learned about chemical reactions in the past. But this also describes a reverse reaction where C and D react and reform A and B. So this single equation describes a system which involves two reactions: the forward reaction moving from left to right, and the reverse reaction moving from right to left. Let's now go back to our definition of chemical equilibrium. Recall that in the definition, it described a chemical system where the composition remains constant. Now you might ask, well, isn't that just describing a reaction that is stopped? Well, this is an important distinction with chemical equilibrium. Chemical equilibrium may appear on the macroscopic level as if it's static or is stopped, but on the molecular level, the reactions are still going. It is dynamic. The reason why the composition of the equilibrium system remains constant is because when the system has reached chemical equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So looking at our theoretical example again, for our chemical system with the forward reaction A and B forming C and D, and the reverse reaction C and D forming A and B, when this system reaches equilibrium, the rate of A and B being consumed to produce C and D is going to equal the rate of C and D being consumed to produce A and B. Not all chemical systems can reach and maintain equilibrium. In order for systems to be able to do so, they must meet certain criteria. The first criteria is that the system must be closed. This follows directly from our definition. If the composition of the system is constant, then we cannot be losing or gaining moles of the chemicals involved. So we must have a closed system. If a chemical system involves a forward and reverse reaction, the reaction itself must be reversible. And not all reactions are reversible. A good example of a reaction which is not reversible would be a combustion reaction. There is a forward reaction where the hydrocarbon reacts with oxygen, but we cannot combine water and carbon dioxide to reform that hydrocarbon and oxygen. So not all reactions are reversible. Because the equilibrium state involves the presence of all the chemical species involved, we must have an incomplete reaction. For equilibrium to be maintained, as in for the system to stay at equilibrium, we cannot disturb it through any sort of pressure or temperature changes. For example, we can't start heating or cooling that equilibrium system. And if we do so, as you will learn, the equilibrium will shift. For systems that involve gases, we cannot increase or decrease the pressure, as that will shift the equilibrium as well. And our final criteria, which we will investigate further when we learn the quantitative side of equilibrium, is that the equilibrium point, or the system reaching equilibrium, can be done so from either direction or any starting quantities. For example, in our reaction that we've been describing, reactants A and B, we can start with those, or we could start with reactants C and D, or we could start with a mix of quantities of all four of those chemical species in that theoretical reaction. So no matter what we start with, we can always reach equilibrium from any combination of starting quantities of the species involved. Let's end off with a question that we will address in our following lesson. A lot of the descriptions of a chemical equilibrium system describe a reaction which doesn't seem to be changing. And from our macroscopic level, if we're just looking at a reaction, how can we tell that a system is indeed at the equilibrium state rather than just a reversible, incomplete reaction which has stopped? And that will lead us to what happens when we stress an equilibrium system, which will be our next lesson.